Morning. Raise your hand if you did. All right, excellent. Raise your hand if you were in Ian's tutorial. Okay, I'm going to cover exactly the same stuff so we can go home. No, I'm just kidding. It'll be a little different. But it was interesting when we both submitted a tutorial abstract and then sort of compared notes, and it was very, very similar. Now, actually, this topic is broad enough that you could probably spend 2 or 3 days talking about every aspect. So if there is something you've seen before, we'll cover pretty quickly. I have with me a couple of people I'll introduce right now. Francesc Alted, he's the author of PyTables, lives in Valencia, Spain. And then Mark Wiebe, a significant contributor to NumPy, who's finishing school, and he's in Canada currently. Both of them are working with me at a new startup called Continuum Analytics. And they will assist me in this tutorial. They each created some part of the presentation, and I'll turn it over to them when it comes to that point. So the topic that we're talking about is speeding up Python. And it's a topic that's been in my thought process for a long time. Having come from the scientific background and dealing with large data sets, I started with Python using 5-dimensional data sets from MRI images, and needing to do basic image processing on those data sets. Now, obviously, I wasn't going to write for loops in Python to do that. So I've been looking for how to speed up Python for a long time. But before you start optimizing anything, it's always, remember, it's good to quote Donald Knuth once or twice in your day to get a good start in it. We all know this aphorism, this couplet, premature optimization is the root of all evil. And very, very true. There's a lot of stories that you can tell. I actually found this guy from Microsoft, where he's a Microsoft MVP, means he helps out on the mailing list a lot. He knows the Windows stack up and down. He's written a couple of allocators. Definitely optimized a lot of code. I like his quote, optimization matters only when it matters. And then when it does, it really does. But you can spend a lot of time chasing down, trying to optimize something that you really didn't need to optimize, either because it's not running very much, or it would have been better spent finding a different algorithm, going and trying to figure out a different way to do it, as opposed to making your code faster. So it's important to have data whenever you're doing this optimization. Now, it's true you're going to be creative, and your experience is going to drive you in different directions to try to optimize, but you always want to have the truth of data driving you. So a couple of stories that I want to tell about optimization. You've got to optimize your algorithm first. Before you take a look and say, hey, I've got this cool thing I'm doing, think hard about what the data is, what you're doing on it, maybe all of the pieces of your algorithm you're pulling out. Python really makes it easier to optimize your algorithm. Makes it a lot easier. You can try a bunch of stuff really quickly. You can try a hash table, you can try a different kind of sorting algorithm. Take advantage of that. Do that. That's the value of Python. That's why, in fact, Fernando Perez told this story once. He was in a graduate school in Boulder, and his professor, they do large physics codes, solving ab initio quantum electrodynamics, I believe. And they all did it in Fortran. Of course, most hardcore scientists still use Fortran because that's the language of the gods, supposedly. That whole lab was just hard-nosed Fortran, and he was going, oh, we've got to go to Python. Python's so much better. And they're like, Python's slow. It's interpreted. How can we possibly do that? He finally convinced his professor when he showed up one day with a faster code. His Python code was faster than their Fortran code. Now, it wasn't because the JIT compilation, it wasn't because they were running on PyPy or anything happened suddenly overnight. It's because he was using a better algorithm, because he could figure one out, because he had more data structures under his control. He had more ability to play around with data. So definitely take advantage of Python. When I was in grad school, I wrote an MRI simulation. I actually pulled a bunch of old Macs together. I don't know why I did this. You do insane things when you're in grad school. I pulled a bunch of old PowerPC Macs together, put Yellow Dog Linux on them, strung them together, and made the Orchard, right? My first large-scale computing device. I guess I got in trouble for hacking into the Mayo Clinic computers, trying to figure out which computers I had access to. Security pulled me out of class one day, and so I figured, well, I'll have to build my own cluster that I know I can have access to. So I wrote this MRI simulator in C++ originally, thinking, okay, I'm going to learn C++, made it really nicely object-oriented, all these cool things inside of it. And it turned out it was really slow. I was so abstracting so many things away that I couldn't really figure out what was going wrong and why things were slower. About 3-4 months later, I rewrote that whole simulation in Python, and it was faster than the C++ algorithm. Now, again, not really because the bytecode is faster than machine code. It's because I was doing something different. I was organizing my data differently and playing with better algorithms. So that's one important thing. Another important message is Google is your friend. I think Google has probably done the most for code reuse than any other software engineering paradigm. Just having a search engine, you can go find something. Has somebody done this before? I know many of you have shared that experience of trying to figure something out and going to Google. And probably some of you have also had the opposite experience of not doing that first, going off and coding yourself. This is really cool. Spending hopefully not more than 2 or 3 days. And then coming back and finally doing a Google search and realizing that somebody did this 10 times better than you did 3 years ago. And you could have just grabbed at least the idea of the algorithm, if not the code directly, and use it. So build on the shoulders of giants. Use code if it exists. If you can, and really this takes a lot of the creative part for you is to think, okay, my problem, how does it map to the wisdom of the ages? Just like applied mathematics. How does your problem map to all the logical theorems that have been proved since the ancient Greeks? How do you figure out how your algorithm is similar to other things that have been published on? Now that's the trick. That's really the trick to Google, is to, it's the graph search. Search one thing, find some words, and search on those words until you find what you're really looking for. Code reuse. All right, and then the other key point, I'm not going to pontificate too long, don't worry. But it is important to point these out, because it's not, we're going to go dive into the depths and start working on changing code and moving one code to another. But you've got to take a step back and realize, don't do that all the time. The key point is profiling. So have you learned to profile yet? I think Ian showed you how to profile, right? So let me give him a plug and say, learn, especially on real data. Have you learned to profile yet? Have you learned to profile in circumstances that your code will actually be running in? Important to do that. Pretty simple idea, but I've fallen victim to this all the time, mostly because I like, I should be faster. This is really cool. I have this idea for how to make this faster. Make it faster. Turns out it saves through 1%. This code's still slow because I really didn't affect what the most time-consuming piece was. All right, so with Python, what are our typical bottlenecks? Why do we have even a high-performance Python tutorial? I mean, some of you may have gone to the PyPy session. Who went to the PyPy session? Couple? So there's a big group out there believing that they're going to be able to eliminate this question for us entirely. That we'll always be able to say, there's no need for such a thing. If we do high-performance Python, it's all about algorithms, because the code is just as fast as any other compiler generator. I hope that can happen, and I think it will in small doses for sure. So bottlenecks in Python are when you have a large loop. It's pretty simple usually. Go looking through code and finding a bunch of places where we have nested for loops. I used to have a rule: if I saw 2 for loops, a nested for loop at all, I'd go, that's got to be bad. Now that's not correct. I really should have profiled first, because you can have nested for loops that aren't looping very much and still have decent code. But if you have a very large loop and you're doing something expensive in that loop, what that expensive thing could be is another loop, another set of nested loops. A function call. Function call overhead in Python is, at least a CPython stack, is slower than possibly it should be. IronPython undid that a little bit by not creating the stack frames until exceptions are actually raised, and then recreating the stack frames, because that's when they're actually really needed. And that's one of the reasons IronPython is faster, is because the function call overhead is minimized, is significantly smaller. Dictionary lookups are expensive. They're relatively fast. Hash table algorithm, it's 01. But it is still, an attribute lookup on a string is slower than a pointer offset that you do in a typical C++ struct lookup or member lookup on a structure. And then potentially another expensive operation. Now it's often said that Python loops are slow, but loop overhead is only significant if the loop is doing something very simple. Most of the time your loops are quite often your loops are doing something more complicated. So here's just a simple example of why is Python slow. Let me just get a feel for how long people have been using Python in the room. Who's been using Python for less than a year? Raise your hand. Okay, so we've got a few people just starting out. Who's been using it for less than 3 years? All right, good, thank you. So don't be afraid to raise your hand high. If you raise your hand higher, you might get somebody to come help you, right? So. Who's been raising it for? Who's been using Python for more than or for less than 7 years? Okay, that's probably most of it. And then how about less than 10 years? And more than 10 years. All right, so we got some folks who can teach me a thing or two. Excellent. So this is just a simple loop you might see in Python. For k in range, million, I'm just adding the integers to x. So this is what that translates to, more or less. I mean, you get a 0 object out of memory, store it in a hash table referenced by x, create a list of 1,000 integer objects. Now that means creating a list with another 1,000 objects. Some of those are optimized, some of those integers are already pre-allocated, and you're just pointing a pointer to those, but others you have to create. Enter x range, which is typically the way people write those kind of loops now. And then loop until there are no more objects for k. And in each time, in the loop, you're going to point k to the next integer object. You're going to get the object referenced by x. And then you're going to call this __ add method. Basically make a C API call add, this generic add of x and k. And inside of there, it's going to do its thing. Typically what it'll do is it'll have to get a hold of the actual data. X is pointing to some piece of memory, and the actual payload is somewhere else. And so it'll have to do another dereference to get that data. Scope, it's jumping back in memory all over the place. And then I have to unbox k. The idea of unboxing is you have a payload, and then the object structure, and unboxing is just grabbing the payload. It's a term that shows up in any dynamic high-level language. Once you get those two payloads that actually you're going to do the integer on, you do the computation. So that's really what you were after. And there's all this other stuff around it to have the dynamic capability of Python, but so you can do whatever. But now I want to do something, and I got to drill down and do that thing. And then after that, take the result, box it back into a Python object, and then that's the add's finished, store that result back in X. So it's actually a lot of work. If you translate that to the machine instructions that are going on, there's a lot of machine instructions. And most importantly, a lot of jumping around in memory. Right, which on modern computers, it's typically you're missing cache, you're having cache misses potentially, where it's because you're filling up the working set. Now, and you can end up with something a lot slower than it would be if you were to translate that to something, I'm just adding integers. Computers actually deal with integers pretty well. If I just wrote machine code to add integers together, it would be that many lines of code versus 3 pages as equivalent. So I mean, there's a value there. We like that it's slow, because we like the dynamic nature. We like the ability to swap things out. We don't have to compile. We don't have to specify types. We have this dynamic, very easy to experiment with language. So it's a good trade-off, I think, but it does have its problems. Now, NumPy helps with this problem. There's a lot of ways to approach solving this problem of speeding up code or making it faster. NumPy is one of them. It's kind of an approach that it helps in sort of 2 basic ways. One is by minimizing the unboxing that has to go on, rather than having, if you can imagine, a list of 1,000 or 10 or 1,000,000 elements. Python has a list of pointers to objects, and each of those objects has an integer dangled off the end of it with a secondary or at least it's a secondary dereference, or it's close to where usually it's pretty close with the ints. But other objects, it might be farther away. It might be an entirely different object in memory somewhere. So NumPy aggregates all the data together in one blob, in one big chunk, and then has one sort of object pointer to that. So it's all very raw, basic data. There's types like floats, ints, all the basic C types, and then you can combine those together into arbitrary structures as well. So one big thing NumPy does is just give you the ability to deal with a large amount of data without all the intermediate unboxing and boxing. Okay, so that's nice, because that's one of the things that causes slowdowns in tight loops, is all that moving around. Then the other thing it does is it gives you sort of a set of pre-generated loops, of pre-generated compiled loops. So let's see. Now, if you want to try out code during this tutorial, hopefully you have a Python environment that you can play with. If you don't, you can go download EPD-free, and it has basically what you need to get started. And I do recommend the IPython notebook. If the latest EPD-free, I believe, has a version of the IPython notebook, but the one I'm using here is the dev version. It's the out on GitHub. And I like it because the header it doesn't take up so much space, all this cruft on the side, so I like it a little better. So this is right out of the branch of IPython. So now who has used NumPy? Raise your hand if you've used NumPy. I was hoping most of you hadn't used NumPy, because I really didn't spend a lot of time kind of going into detail about the NumPy. If you want to, that's one way to speed up your code, is just to look for ways you can use NumPy. You'll hear a term, vectorize your code, and we'll talk just a little bit about what that means. It basically means use these building blocks. So in NumPy, there's a bunch of code, there's a bunch of functions like sign, there is power, nope, it's pow actually. Power, there is add, and what these do the nice thing about the notebook is you can save these notebooks out into a file, and then someone else can load them later, and you can see the kind of what happened. So A now is this, if I print it, it's this array from 10 to 1,000. 50, by default, it uses 50 points, so it equally spaces those data. And then it looks a lot like a list, except in contrast to a list, it's just representing a big chunk of memory, 50 floating point values all stuck together in a single block that you can then stream over really quickly and do calculations much more quickly than you could in Python directly. I can do the sum, and that just actually invokes a C-level loop that loops over that data really quickly. Sort of a precompiled loop that it'll use, rather than the equivalent in Python would have been to use the sum generator, which I can also use here, although there's a big difference between the sum method of NumPy, which is using essentially floating point arithmetic on that chunk of memory, and the sum generator, or the sum iteration reduction in Python, which is asking for an element. It's essentially asking for A0 and grabbing that object out, then asking for A1 and grabbing that object out. I'm actually curious, with only 50 points, only 50 data points, I don't know how much different the times will be. So that's not bad. Usually I like the number to be a little higher. So it's a little bit faster at that many data points. There is some overhead associated with getting into the NumPy pointer, figuring out which, there's a lot of data types NumPy has, and you got to figure out, I got to get to the float and find the float function and actually use it to reduce across. So there is some overhead there, but if I up the number of steps, let's change A. So it's actually 10,000 steps, right? So now notice NumPy prints the dots, so it doesn't go forever. But now we should see a bigger difference. Still pretty good, actually. Yeah, I'm a little surprised because I know that A0 grabs a NumPy vect scalar, and if sum is just doing the add on that NumPy scalar, it's going back in the machinery quite a bit. So that's a little surprising, but that's not bad. Yeah. To do
the same example, my machine is 10 times faster to do that.
with the sum is 10 times faster, or the sum?
Mine too the NumPy did much better than Python sum.
Oh, thank you. Sum is Pylab sum. Ah, yes. It's exactly the same sum. That was the first quiz. Very well. You passed. You got an A. Good job. Very well done. Yes, that is an unfortunate side effect of the sum existing in NumPy before they added it to Python. I can go back and get the real sum. How do you do that? It's built in?
Yeah. Well, del sum might also.
Oh, del sum. That's a good idea. Yeah, there we go. There, okay. Now that it did fewer loops, and it's 4.68 milliseconds as opposed to 14 microseconds. Now, you'll also notice, this illustrates another point about NumPy. If you use NumPy, you need to use it for its vectorization property, not for its ability to contain objects. Right? Python lists are actually very optimized containers of arbitrary objects. So what that means is if you're using NumPy, you create a NumPy array and then you put it in a for loop and start extracting elements out of that for loop. So in other words, if you use the Python sum function on a NumPy array, it's going to be slower than using a Python function on a list of floats. Let's see if we can illustrate that. I'm going to convert A to a list. So you can see that was 114 microseconds versus the 4.68 milliseconds. That's what I was expecting, and the reason is because essentially this operation on B, so adding two elements from a list like that is much faster than adding two scalar elements from a NumPy array. There's some technical reasons for that. It doesn't necessarily have to be that way, it's just that the scalar math has never been implemented outside of just reusing the ufunc machinery, which assumes it does the same thing for scalars as it does for arrays. And so there's a lot of overhead you're paying there. So that's one of the first lessons. If you're using NumPy to speed your code up, use NumPy to speed your code up. Don't use it as a container object and write for loops over it. It'll be worse than just using lists. Okay? All right, let's go back to this notion of vectorization. The idea of vectorization is to eliminate loops, basically. Don't use for loops. Instead, use these pre-compiled for loops that NumPy has. There's for loops. There's ability to mask data. There's sort of a where function. It's a bit of an art. If you're from MATLAB, IDL, you're familiar with this art. It's been around for a while in the array-oriented computing literature and ecosystem. Sometimes there are some things, and quite a few things actually do day to day, that can be vectorized very easily. There are some things that can't be very easily. So my advice is not to, I mean, some people like to play games. They really like to get into, oh, can I vectorize this? You know, here's some complicated algorithm. Let me see if I can make it more complicated by vectorizing it, making it completely hard to read. That's fine. It's a nice pastime. Some people are theoretical mathematicians for their pastime. Sorry if there's any theoretical mathematicians in the room. So you don't need to. Vectorization, if it works, it should work quickly. If you find yourself going into great lengths to vectorize, try a different speed-up technique, typically. And you'll be able to keep your for loop and maybe understand the algorithm a little better still. But when it does make sense, it's actually can be quite nice. So here's a simple example of a sync function. A sync function is an example of something that it has a branch statement in the middle of it, right? So it's actually hard to vectorize, sort of. This one is meant to be interpreted where x is a single floating point value, and I'm testing to see if it's 0, and if it is, return 1. Otherwise, I compute this ratio of the sign to the value. So then, if I wanted to calculate a vector of those, I would have to use some kind of list comprehension, which is the equivalent of a for loop in Python. So evaluate the sync for all that loops. Each of these other blocks are vectorized versions. What they do is they take a whole list, and they can evaluate that sync function can take a sequence to start with, or can take an array to start with. And so you don't have to do this list comprehension at the end to get a vector of values back. You just put a vector in, you get a vector out. So one approach is to actually compute the sign over do the computation everywhere, even at the point where it blows up, and rely on the floating point hardware to put a nan in there or some other crazy thing. And then after the fact, go through and mask out and place a 1 in where the value of x was 0. So at first blush, you're actually doing more computations, right? I mean, in this case, you were not doing the sine x over x when x was 0. So you'd think, oh, I'm saving myself time because I'm not doing that computation. And perhaps there is some, actually not even sure if there's any power savings either. You are doing the computation again, but actually on modern hardware, a lot of times that's better. Because the computers are set up with their branch prediction and their pipelining to do a bunch of calculations at once very quickly. And if you have to break that up, and all of a sudden there's a big if statement in the middle, the performance goes way down. So actually doing it this way by computing it twice and then masking can actually be better. Way back in grad school, I was trying to write convolution. I mean, that's one of the ways I got into numerical computing was I really was writing ND convolution. It's kind of a fun problem, really. Convolution is what happens when you, in the time domain or the spatial domain, when you multiply in the frequency domain, right? So think about trying to implement that in the spatial domain or time domain. How do you do this convolution? If it's 1D or 2D, 3D, it's pretty straightforward. You write nested loops, and we'll see an example of that later. If it's ND, how do you write n-dimensional loops? I mean, I guess you could write them on the fly. Anyway, that's what got me into doing this. And I wrote a little, so to start with, I wrote a 2D algorithm. And inside of this deep nested for loop, I wanted to check for boundary conditions. And so I had a big if statement, right in the middle of this big, nested for loop. If it's near the boundary, do this. If it's not, do this. And performance is horrible. Yeah, it's actually still there in SciPy. Kind of embarrassed about it because fortunately somebody came along and wrote ND image, which did much more sane things on the boundary. Did not try to big branch and a big if statement and make the pipelining, the beautiful pipelining architecture that Intel has laid out completely empty and spinning for cycles. So it works much, much better. So that's one version of vectorization. The second version, it's similar, except it uses this where clause to basically compute. Instead of computing twice, it computes, it calculates this PIX and changes that number to be either, it changes it slightly away from 0. So it's kind of a specialized vectorization. This is a general vectorization. It would work with sort of any algorithm. You just take out the pieces that are 0 and calculate those differently. Down here, you're sort of using some property that you know. I know the sync function approaches. The problem is at 0. If I just move away from a 0 a little bit, I'll get an answer that I'm okay with at the limit point. So that's that approach. Replace the x's or 0 with a tiny number instead, and then just do the calculation. Another approach people take.
Travis?
Yes?
Another point about vectorization, you mentioned there are reasons not to do it sometimes.
Yeah.
The other one I didn't get to in my talk this morning is when you've got an embarrassingly parallel problem, like the Mandelbrot set, with the perfect case for vectorization.
Yeah.
The problem is that some of the calculations are an awful lot of the time. Most of them require very little amounts of time.
Yeah.
As a result, everything has to be calculated all the time. And even though it's running at C speed wonderfully fast in the background, overall you come off worse off. And that's not obvious at the beginning if you don't think the problem through, even though it looks like a perfect case for vectorization. Yeah,
it's and maybe, I don't know how you think about it, but sometimes if the problem separates, is very separable, and there aren't sort of if statements in the middle, it's when you have this graph that you have to okay, I'm going to calculate, or I'm changing the calculation based on other data. If the calculation changes based on data, it can be hard to vectorize. To do it, you essentially compute more than you need to and take up more memory and more time. Now that may not matter, but it can, for certainly the Mandelbrot set as an example. So this, there are literally thousands of web pages. I mean, the MATLAB community talks about vectorization. It's the same concept there. It's really just trying to get rid of for loops. I guess I would say it's a really good thing to do and to learn about, but it only goes so far. And I honestly would like to see a day where it's not so relied on. Maybe it's relied on just for constructs that are clear, like reductions, or where it actually makes semantic sense to keep it vectorized. It lets you think about less, right? A lot of times now in high-performance computing, rather than thinking about the problem you're solving, you very quickly get down to okay, here's the loops, and where's my pointers, and and you sort of get lost in the problem you're solving. That's very nice when you can have a set of libraries that are optimized, and you can think at a high level. Oh, I'm going to convolve this with this, and I'm going to take that and multiply that matrix by this matrix, and just let the building blocks of high-performance computing kind of pull it together and stream it through the processor better. I mean, that's the ideal. That's the kind of software I like to use. It's the kind of software I think we should try to put together. Kind of get rid of for loops, but not necessarily with the same concepts of vectorization. All right, so what I thought I'd do is walk through a simple example. I'm going to turn, I only have, let's see what time it is actually. I'm going to make sure we're keeping track of time a little bit. I'm going to walk through an example that illustrates kind of going from here's some code I want to make faster, here's how it does in Python, and here's several other approaches to do it to make this code faster. It's sort of teaching by example, I guess. So the problem is to take an image and then do a convolution filter on that image, take this kernel, which is a discretization of the Laplacian operator. Laplacian is a second derivative. It's the second derivative of x, second derivative of y added together, basically. And and it's a negative of that, actually. But it gives you, it sort of finds the second derivatives, and that turns out to be an approximation of the edges. Second derivatives are high where there are edges. And so if you apply this derivative filter to an image, you get an image that looks like edges. So we're going to do that multiple times. So what I have to do is I have to take this 5x5 kernel, go to every point in the image, and mask it on top of a local element of the image, multiply those values by the underlying values of the image, and then add all that up and get a number. And that's what I replace at that point in the image. That's my output value for that point in the image. So I put it there, and then I shift it and do it again. Right? So I'm going to basically have four loops. Right? I'm going to have a for loop that goes over the whole image, and then inside of each kernel, I'm going to have another 2 loops that go over that kernel, and they'll multiply. So not very difficult algorithm, but you can appreciate that if it's done in Python, you're going to have, it might be slow. So we're going to look at 7 different approaches to doing this. Yeah, question? Yes, it's x, y, which are the image dimensions. So x, y, and then if you want to call these u and v, yeah, it's those dimensions. So I'm going to do 7 approaches. The first is to actually just use that wonderful function I told you about that someone contributed to SciPy in ND image called convolve. This is not the slow one that I wrote. This is the better one. So that's all the slides I have. So we're going to go to now a notebook where things are exciting. All right, so I have here a notebook. And inside the notebook, and you can basically follow along. If you'd like to type this in, I'll go slow and give you a chance to do that. So I'm doing this filter. So that just defines a filter. Let me actually restart the kernel so we start from 1. So we're in a fresh. If you don't know the IPython notebook, basically there is an underlying kernel process, and then I'm looking at a view on that kernel. And I can have multiple views on the same kernel. And if I were really clever, I could point you all to it, and you could all see the view on your machines of this kernel. But I'm afraid that might also bog my computer down. Okay, so notice that because I restarted, the output went to 1. So this is the first element. Now I'm just grabbing a URL. I'm grabbing this image from this location on the net with URLlib2. One of the neat things about Python is it's integrated with all these great web libraries, and so I can do cool things like that, grab an image off the web, use this cstring IO because IamRead from matplotlib expects a file-like object and not a string, and so I wrap this string into a file-like object with cstring IO, and then it has read methods, and I can just pass that object to the IamRead function of matplotlib, tell it to use a PNG format. Actually, the IamRead function of matplotlib really only supports PNG, I think, at the moment. And then what I get back is actually a RGB image, a 3-dimensional image. And so I wanted to get a 2D image. And so I will take this sum function and sum the last dimension. So I'm just adding the red, green, and blue channels together into a single grayscale. Okay, so that's what this code is doing, axis equals -1. Now if I take a look at this, it's just lovely turtle, which shows up actually with an interesting pink tint. Curious on the projector. I don't yet. I could put it there, actually, pretty quickly. How far?
Yeah, there.
Perfect, okay. Actually, I could put this pretty easily. Let me see. So this is the fast Python. I will copy this to okay. If you go to this, you can get that GitHub. You can see that a little bigger. It'll just be in the top level directory. Now, if you start the IPython notebook in the directory where those notebooks exist, then they'll load up automatically. Okay. If you lose track, you can go to Continuum.io, or you can go to my web thing, and you'll see the Git where I've been pushing things recently. You can find it that way as well. Just go to my TE Elephant GitHub page. You'll be able to find it that way. All right, any questions? So I'm just showing this image, and I'd like to actually, so remember I said build on the shoulders of giants, use code that does what you're trying to do instead of writing new code. So this is a use case. I want to do a convolution with the Laplacian filter. That is a very well-known image processing technique. It exists inside of SciPy and the image as convolve. And so I just call convolve with the image and the filtering kernel, a 5x5 kernel. And it comes back with an image, and I can look at it, and sure enough, it is the edge image. So I would recommend that you at least get this image and, or some other image. If you want to use SciPy Lena image, you can do that, just so you can play with some of these codes. It really does help get your muscle memory working and helps connect things. One of our weaknesses as humans is we have this thing called confirmation bias. We think when we hear something, we know it, and we start to look for reasons why we think we know it. But very clearly, very often, if we just hear it, we think we know it, we don't pay attention to it, we actually don't. We haven't learned anything. So definitely, if you can type, it'll help. All right, so that's the first, is just library code. And second is our Python implementation. Now, if you don't really know what a convolution is, you can look at the Python implementation and get a feel for what it is. Now, it turns out sort of using lists of lists for a 2D array is a little bit challenging. It doesn't quite have the same niceness as a multidimensional array where I can index the elements specifically. So I actually, the first time I wrote this, made the classic mistake of initializing a list of lists using something that looked like this. Right? Which you think, oh, that's so clever, it's going to work, it's going to be really, really great. And then I spent way too long trying to figure out why my code wasn't working and giving me basically a single line that was the same all the way down. Right? When you do this, you're making a single list and just many references to the same list. And so I'm over and over again writing to that one list in different ways. But in the end, I end up with one list, just looked at many ways. Yeah, that was well, especially as I'm trying to figure out the indices here, and I'm thinking that's where my problem is, but it isn't just in that error there. So what I had to do is actually use append. There may be other ways. Does anybody know of a good way to initialize a 2D list like that other than kind of growing it, other than a NumPy array to list, which is also in a, when you're in a sticky can do. All right, so this is just taking the image, it's getting the lengths. This, of course, assumes these are regularly spaced. Then I'm dividing by 2 so I can get this, the boundary, basically, because I kind of jumped over, what do I do with the boundary? If I have this 5x5 image and I go all the way to the end, what do I do for the boundary values? I am doing what every sane person does and ignore it. I'm just kidding. There's lots of things you can do. But it's very easy just to not go there. Right? If it's hurting, don't do it. So don't go to the edge, just stop. And so that's what I'm doing with this if statement, is just don't do this inner loop if I'm too close to one of the edges. So here's the outer loop going over the pixel images, the images of the pixels of the image, and then for each pixel in the image, here's this inner loop where I'm going over the elements of this filter. And then I'm taking the elements of that filter, they're actually reversed, convolution reverses the elements, kind of takes a symmetric copy. Now in this particular case, this filter is symmetric, it wouldn't matter. I could just say filt II and filt JJ. Multiplying one of the values from that filter from another value from the image. Adding those together. And then when that for loop is done, that nested for loop is done, those 25 elements are all added together, multiplied and added. I append that number to this list and then go back and find another pixel and do the same thing again. So there's 4 loops here. Now inside of each of these loops I'm actually not doing that much. Right? The very core here I'm not doing a whole lot, I'm multiplying some numbers. Right? Machines are very fast at multiplying numbers and adding them together again. So that's one of the reasons this is really a prime candidate for being sped up, is because there's a lot of overhead in a couple of things. One is this indexing. I'm grabbing into a list and then grabbing into another list from there. So I'm doing 2 indexing operations, 4 indexing operations, doing a quick multiply and then the overhead of this loop. I'm also, stupidly using range instead of X range, although it probably doesn't matter with these sizes, they're not that big. If I run this code, a couple of things. One is my image, when I read it from Matplotlib, is a 2-dimensional NumPy array. And I can run this. NumPy arrays will accept this kind of indexing. You can treat them as if they're just nested lists. But as I said before, that's going to be slower if you get down to a scalar. It's actually not too bad if you just stay at, if you index into a 2-dimensional list and get out another 1-dimensional list by getting just the first element, that's not too bad. But if you get a scalar and then do math operations on it, that's where the problems are. That's where NumPy is very slow. So instead of handing it this NumPy array, I use the toList to get a list and then pass that into the filtering operation. All right, so that I have a little spreadsheet that shows these times. Later I will, and I don't think this responds to the nice, yeah. See that a little better? So here's the Python. It took 38.1 seconds to run this code. And here is the SciPy. So I'm actually showing you the very fastest in the end, at least on this machine, and the very slowest. And you can see that basically a 4,000x speed up, going from pure Python to a convolution kernel that was written in C, did some nice things with point arithmetic, in half a second. So there are, you can imagine if this convolution kernel is in the middle of your algorithm, a lot of times edge detection isn't everything you wanted to do, it's just the start of what you want to do. It's what you're doing to do many other things. That you've got to optimize this. You can't be just using Python code. So actually this illustrates the reason the whole SciPy library exists in the first place, is to give you these building blocks to do this kind of work at a high level and make it fast so you're not implementing Python. It also illustrates why PyPy is going to get speed ups. If you can really convert those for loops for particular data types to fast code, then it's going to be great. But I'm expecting 4,000x speedups, right? I'm really not going to be that excited until I see 4,000x speedups. So that's what we need for the kinds of problems we're solving right now with SciPy and NumPy. All right, so here's an example of vectorizing. You might take a look at this code. Now, how would you vectorize that code? Now, what does it mean to vectorize that code? It's probably worth thinking about just a little bit, maybe drawn on a piece of paper and trying to think, what would I do? What does it mean to vectorize, first of all? In simple terms, it means to get rid of for loops, right? Replace them with array operations. Yeah?
Can you somehow like take and set and do an operation on two matrices? Instead of going in and doing it one at a time, just do comparison of two matrices?
Yeah, you could. There's actually there's a way to map this into a very large Toeplitz matrix and do a matrix multiplication that would do equivalent convolution. Yeah, I didn't do that one. Didn't do that approach, but that is true. Spent a bit of time thinking about how to unravel that 2D to a larger 2D. But you're going to use a lot more memory. Although in this case, maybe that's not a big deal. These aren't big images. That's not a big deal to do it that way. Yep, that's right. Somehow you got to, so that would get rid of all for loops, all four for loops, and just give you one dot product, right? Plus a reshaping kind of tool. That's a good idea. Another way, which is a little simpler, is to kind of think about it as, think about each of the elements of that filter. And essentially what I'm doing is I'm adding together other images. I'm taking an image and shifting it. Let me see if I can illustrate this with a simpler problem. Let's do, one nice thing about this IPython notebook is I can get a console up that talks to the same kernel. So, did I not execute this code though? Yeah, so I executed in the window and now it's available in this other kernel. But let's, so I just want to take a look at a sine function and think about calculating a simple filter on this. So instead of a two-dimensional problem, I'm going to do a one-dimensional problem and just think about convolving this with a simple 1 for 1 filter, right? So that's basically taking, it's equivalent of taking taking a 4 and multiplying it by one segment, and then shifting and multiplying that by 1, and then shifting again and multiplying that by the final element. So I take my kernel, and instead of moving it around, my image, I take the kernel, fix it, and move my image around inside the kernel, right? And now those images, I can think about doing the multiplication by that whole image at a time, and just do a single scalar times a whole image, and let NumPy do that underneath in a very fast C loop, and then just take that image and keep adding it. So I take what would have been multiple for loops and turn into 3 additions. So that's what I'm doing in this code, is taking, and I'm looping just over the filter size. So I'm just doing the II loop. And the outer ij loop, which is in the Python code, is now embedded in this addition right here. So image, I'm selecting a slice. This is using slice notation in NumPy to take, this is the starting slice, the ending slice. And let's see if I can't print shape, right? And you can see that it is taking the center piece. That original image was 350 by 490. Now every time through the loop, I'm basically taking 346 by 486 size images and adding them, multiplying them by a value, one element of the filter kernel, and then adding them together. So they're shifted versions of these images. I'm moving the image around, multiplying it by an element of the kernel, and adding them up. Yes?
Can you go back to the very first Python version?
Yes.
Because we use a range, I will use X range. I would put the range inside the loop. If you change the range, just the range from the constant, it takes the range out of the loop. Because now in the inner loop, you're allocating a list all the time, which is kind of expensive operation. If you take it out, you should get quite a bit.
Well,
Goes into a range. And
yes.
you put it in the inner loop.
Oh, this one right here.
Allocation with range.
Yep.
But it's equal range and if it's constant, so you can do this X range object outside and use the X range object. It could make it quite faster. I got to.
Yeah, that's a good point.
Allocation is something that takes time. So you could say X, you got range, X range. I will use X range all the time because you don't need the range. You don't need this.
Sure, sure.
Yeah.
Yeah.
In addition, it rebuilds the integers every year it does it. I think he wants to use range so the integers only get created once. That's range.
It's just use range for looping. It's not just use for looping. It doesn't need this range.
I'm just saying.
So there, I really need to do that one, but I'm sort of,
Yeah, because if you're allocating this, I don't know how time to do it, but it's very expensive. Allocating it to enough.
yes, that is true. That is true. I timed it down here. Let's see if the, well, I think I got rid of that timing because it was so long. Yeah, that'll certainly be faster. Thank you. Okay, so I won't spend any more time on that vectorization concept, but it is, there's several ways to do it, but that is, you're sort of looking for ways to do array-oriented operations. Add whole arrays together at a time, rather than looping through them in Python. Let C do that by taking advantage of the element-by-element calculations that NumPy provides. And now there's another tool. If you're not going to use NumPy, there needs to be, and you're trying to get speed ups, you have to use something else. A lot of people will just go to extension modules, and they'll write code in C. Python's been very, very good at gluing code together for a long time. And so you'll quickly go to an extension module and write your code in C, then pass your data in, and then let C handle it. Let your favorite compiled language, whether it be C or Fortran or C++, or there's quite a few others these days. Weave is a nice tool that lets you basically not worry about all of the glue around, right, in an extension module. Perhaps it might be worth taking a look at the pure C extension module, actually, at this point. If we were to go to, this is sort of the bare bones, minimalistic C extension module that implements this one function. Right, really has all the pieces needed, even for doing both Python 3K and Python 2. Let's see, I don't think I can. I want to make this bigger. Yeah, this is not doing that, unfortunately. Shows the people that were the PyData. Go back to an editor that I know works if we do that. So there's a little bit of messiness down here at the bottom because in Python 3K versus Python 3 versus Python 2, how you write a C extension has changed. In Python 3, you define this py init method. This is what the platform dynamic loader is going to call, and this function is responsible for essentially creating all the methods of that class, of that new extension module. A C extension is essentially it looks like a Python module. If you import it, it can have methods, it can have functions you're calling, it can have new classes, but if you try to look at the source code, it doesn't exist. You're basically emulating those or writing those in C. But this function is what sets up all those name mappings between the Python method name and what gets called at C. And it does it with this module def. How you spell it is a little different in Python 3 versus Python 2, but it's the same basic idea. These lines of code are necessary for NumPy. If you're going to use the NumPy C API, you have to say in your initialization module, import array. If you use the ufunc part of it, then import umath. This is the magic table. It's a little bit different in 3K or not. You can see I only have one method in this extension module. It's called filter2d, and it maps to this C function. So every time in Python I call filter2d, it's going to give control to this function, which has this signature. Self is used when it's a method on a class. Otherwise, all the arguments come in through this PyObject arg, which is a tuple, and you can do whatever you want from there, right? So it hands control to you. You have this args tuple, which is in Python, and whatever you want to do, you can do. And then when you're done, you just have to return a Python object of some kind. And if you want to return more than one object, you return a tuple. Now the rest of writing C extensions in Python, it's pretty straightforward. You write methods you want to call, and they all have a similar signature. There is a signature if you want to support keyword arguments. You can have a third argument passed in, and you just identify that in the method definition table with a separate, instead of using meth var args, there's meth var args, and you OR that with meth keyword args. The best thing to do is to use Google or use another extension module, that there's plenty of them that are out there, and go grab one. My first extension module I ever wrote was a I/O reader for NumPy called NumPy I/O, and I did it by looking at somebody else's code and used their example. Somebody had written table I/O, and I just sort of, oh, this is how you do it, and cut and pasted, and off you went. Right? That's it's a good way to go, right? It's a lot of template, it's a lot of boilerplate code. In fact, it's so much boilerplate that most people today don't do this. They'll use a tool like Swig or like Instant or Shedskin or Cython or Weave or any number of tools that have essentially created all this boilerplate and let you focus just on the piece of code you care about, which is that piece of code sitting somewhere between I parsed my arguments, maybe done some checking on the types to make sure they're right, and now I'm here. Now, what do I want to do now that I have these input arguments, and now they're actually C, they're things I can play with in C? Now what? Well, it's pretty straightforward what I want to do in this case. I build an array of zeros. This is a PyArray zeros is a NumPy C API. It builds me a NumPy array of zeros, and I get the M and N shapes, really the same algorithm I had before. The spelling of how do I get a hold of the ijth element of an array is a little more complicated. There are ways to improve that, but this is sort of the generic way to do that, is you use this, you basically use the strides array and do a multiplication, a calculation. That's wrapped up in that macro for 2 and 3 and 4 dimensions. So it's a little bit easier. But that's a bit messy. I would argue that's not very readable. Like, you can kind of see your way through the same code that was in the Python code. But it actually took me a lot longer to get this code working, between semicolons and compiled steps not working and missing an NF and having the thing segfault because I was going out of bounds. I mean, it's why people like to use something like Cython, because you can get really good performance and not have to write low-level C. But you can if you need to. And it should be emphasized that whenever you're using CPython and you're using one of these tools, all that tool is doing is building this code for you. Right? At the end of the day, that's what you're getting, is something like this. And a compiler is producing an extension module. That extension module is really just a shared library. And Python has the ability to load a shared library and extend its runtime with this .so or .dll. It's actually PYD on Windows, but it's the same thing as a DLL, just with a little bit of different entry point and conventions. So you're setting yourself up to just extend the system in a very particular way. So that is, we'll come back to that in a little bit, but that just gives a little precursor to Weave. Weave is a way to write a C extension without all the boilerplate. You basically just give it a snippet of code in C syntax as a string, and you pass that code into, there's several ways to use Weave, but one of the easy and popular ways is to use Weave.inline. So here's my snippet of code. I have my outer variables that are the shapes, and I have the loop variables, and I have this double. And then I just write standard C code. There's a couple of things that are unique about Weave. One is that it understands arrays, understands NumPy arrays, and so whenever you define a variable that will cross the boundary between Python and C, which I've done here with image, filt, and result, it defines for you, basically in the header, in the boilerplate header that Weave creates, it defines a bunch of macros for you. So those macros are available for you in this snippet of code. And it also defines a few variables. One of those variables is a capital N with the name of your variable. And that capital N with the name of your variable is a C array of the dimensions of that array. So that's why I'm extracting the 0 element and the 1 element to get the MF, NF, M, and N, the shape of the filter and the shape of the image. I need those values to set up my for loop correctly. And actually here this code isn't quite right. It's hard coded to 2, which I later fixed in other pieces, but not here. This should be basically should do integer division. This number isn't just always 2. Okay, and then the other, so you have these basic arrays available for you. It's very handy that way. It can be very nice to do sort of, I just have a piece of code that I need to make fast, and I know how to write C, let me do it. Now, if you don't know C, maybe it's not worth learning C, right, to use Weave, right? But if you know C, then it's like, yeah, absolutely, I want to use it. Most people today, if they don't know C really well, they'll reach for Cython, right? Because they know Python, and Cython lets them speed up their Python, and so they'll reach for that instead of going to Weave. But there's a lot of people who still like C. Yeah?
With all these array operations, is there any OpenMP?
So NumPy does not actually have any, well, at least not, there may be people who have done their own builds of NumPy that try to use OpenMP. Currently, I don't know of a runtime that uses OpenMP. Now you do have, what NumPy does use is vendor BLAS, like MKL or Goto or Atlas, and so dot products are as fast as any other array library. But there's a lot of opportunity for speeding up and taking advantage of parallel code. And actually, when I turn to Francesc, he'll talk about how to speed up with parallelism and approaches to doing that.
And I showed in Cython this morning how to use the p-range operator.
Excellent.
The OpenMP support.
Excellent.
But it's only one line of code change once you know what's going on.
Right, right. No, so actually, because of that, there's a lot of opportunity to do things faster than NumPy's doing them, right? If you had, there's a lot of opportunity for that. So, a lot of low-hanging fruit, actually, with the modern OpenMP, OpenCL, you take advantage of GPUs.
Travis, can I just ask, how many people use C? How many C codes in it? How many Fortran?
All right. Fortran, okay, so yeah, significant amount still. I think we're still at a place where to really take advantage of faster Python, you do need to still know C. Maybe we'll get to a place where that isn't the case in 5 years or fewer. I don't know. The other thing that's slick about Weave, hackish, slick, I don't know, it depends on your point of view, is it also creates this define with a capital letter. So you notice that filt is all capitalized, image is all capitalized, res is all capitalized. It came from, I passed those were the variables I said they're going to be available in my Python namespace, and that I want you to pass them into as arguments, essentially, to the C function. So they're available inside of here. But using this macro lets me use parentheses to access the elements. Like rather than using that PyArray get pointer kind of thing or doing the strides arithmetic myself to get to the element I want, I can just use these macros and get exactly the element I want. So it's fairly easy to read. Question?
How does it compile the line? Does it need to have a compiler ready?
It does have to have a compiler available, yes. It uses it reaches first for a compiler that Python was built with. There are options to Weave. You can tell it which compiler to use if you want to override that choice. But yes, it does have to have a compiler available. Just like Cython has to have a compiler available too. This is the same code, and it runs a bit faster. Okay? Yes, we're getting the same output with the same input. I do have a Cython implementation here. I won't spend a lot of time talking about it, as you talked about this morning. But it's basic. Looks a lot like Python, except these CDEFs. Defining this as an ND array with double type and ndim equals 2. Actually, during the course of preparing this, I forgot to identify this division, this variable mf2, as a CDEF unsigned int, which you can see actually is still forgotten. I changed it in the I changed it in the actual code. This is simply a cut and paste from the code that actually is compiled to run this. So I forgot that, and I noticed that it was really slow. This was taking a long time. And I thought, this is really weird. This should not take so long. But that's the thing Cython does. It will sort of run arbitrary Python code. But then that's where the annotate comes in handy. You just show them the annotate so you can see what is actually being replaced and what's still at the high level. It's kind of a nice tool, actually, to learn what takes time and what doesn't take time, and what you can speed up and what you might not worry about. So once I defined those as CDEFs, then this sped up, and I got the code I wanted. I will show this is the setup.py script that I used to build both the Cython extension and the pure C extension. So filter2d was the pyx file that was a Python, a Cython extension module, and then the pure C was just that raw C code that you don't see hardly anymore, but you can still produce, and it still does its thing. And there's just the text of that C extension. I think the reason to show this C extension is just to illustrate that it's not, if you don't know C, it's going to be complete gobbledygook, or maybe something just slightly north of that. But you're going to be able to at least see that it's not that much work. It's not that much code to do a C extension. And that's why you find, in fact, that all over the Python ecosystem, there's thousands and hundreds, tens of thousands, I don't know, maybe hundreds of thousands of C extensions, where people have used this to glue their large Fortran, C++, C libraries into a Python harness and into the Python ecosystem. It's a big part of the reason Python's used for science and for fast code, is because of this ability to glue lots of different languages together. C has kind of it's played the role of this sort of platform for code reuse, this place where everyone can go and their libraries will work. C compilers are sort of ubiquitous. It definitely has kind of become that. We'll see if perhaps, it probably will stay that way for a long time. All right, so quickly, so we can turn some time over to Francesco, has some interesting things to show you. My final example is actually a Fortran example, for those who like Fortran. I actually really, this is my favorite way to write optimized code currently in Python. My new favorite way is going to be what I show you after Mark's done, but it's not quite finished yet. But this currently is still my favorite way. Fortran is a really nice language, and it's really simple, really straightforward. It's got complex numbers. It's got a lot of high-level things you really want as a numerical programmer. And F2Py makes it dirt simple to wrap into Python. You just write Fortran code as a subroutine, and then with this intent out, intent in, which are actually Fortran 90 constructs, F2Py will build me an interface that does exactly what I want. It has the M and N are no longer part of the interface. It just uses the image1 and the filt, and the result is an output. So it gives me exactly the same interface as I had with all the previous ones, except I could sort of get in and write relatively fast code. So that's the Fortran and it gives the same result. Now I did some timings, and this is the timing I got on this machine under these approaches. Obviously the Python could be improved, as we saw, maybe even probably, I don't know, 4x perhaps, I would imagine, maybe even 5x. But the fastest, I think one of the lessons is the fastest code was SciPy Convolve, right? I wrote all the, which is a good lesson to learn, I think, because if you ever have a complex work to do, it's best to use library code. Somebody's probably thought about how to make that optimized, rather than try to spend time yourself optimizing it. I got pretty close with Weave. In this case, Cython didn't do that well. I haven't really explored with, maybe I didn't have an optimization turned on. Usually I've seen Cython get closer. In this case of a double loop and using the buffer interface, I'm not sure actually. I don't know kind of what the code emits. Weave is just going right to the bytes and just doing a pointer arithmetic and grabbing the bytes and doing a dereference. It's sort of the fastest you could do. The pure C is really close. It's actually interesting. It's not quite the same. It's the same as Weave. And then NumPy is this baseline one. The Fortran solution is also usually faster. That surprised me here. Could be something there. So it's an example of kind of trying to speed up Python. I think the lesson is use library code. If you know C, it's still helpful. Cython gets you a lot of the way there quickly, but it still takes some effort and some guidance. Later, I'll kind of, just to get you, I really would like to see this though. Like I'd like to see the ability to just take this code. I want image and filth to be erased, and I want to just write that Python code and have that be fast. How do we get there? How do we get there? Francesc, you want to come and take over, and I'll come back and talk a little bit later. We'll have Francesc will talk a little bit about NumExpr and just a bit on Cython. Yeah.
Just a final question on so you put the numbers up. A point I touched on this morning is also the trade-off with the support time you have to put in. So with Cython, the annotated code, you've got to look after that code and the compilation environment. ShedSkip makes that trivial, but then you've got to have some of your code separated out. Do you have any thoughts on which is more?
No, that's a good point. That's a good point. It depends on, if you take someone who knows Python and C, the Weave code is actually pretty maintainable because it's inline, it's right there, it's available. Now, if you don't know C, then it's not. Then it becomes this, I don't know what this is even doing. And then the Cython code becomes a little bit more easy to maintain. I think the NumPy code is pretty maintainable, right? Because it uses very constructs that are well known. And then if you're a Fortran shop, so it kind of depends on who you are. But I would look at NumPy and for this particular example, I knew this was the case. I knew convolution is a well-supported concept. I would just use SciPy Convolve. That's the most maintainable code, right? Use libraries where you can, and then after that, probably Weave. Given me and depending on the team I had. Anyway, so Francesc, you ready?
If you could please repeat any comments or questions from the audience. We've only got that source.
Okay, yeah.
I forgot to tell Draft.
Yeah.
Anything they tell you, please repeat it, otherwise we won't be able
Yeah, sure. Yeah.
Could you
Sorry? The volume? Can you hear me? Yeah. Okay, so during my part of the tutorial, I will be talking about NumExpr, which is a library to enhance NumPy operations. And also, I will mention briefly Cython. I will not talk very much about Cython because Ian already has done a good coverage of Cython. But I will mention it just for comparing Cython speedups and NumExpr speedups. Okay. You can find the exercises materials. You can download them from this URL. So please, if you... most of the material here is for the Cython part. So for the NumExp, we will just need the IPython interpreter console and the NumExp library. But you may want to use the Cython code maybe later on. Okay, everyone has got it? Okay, so, well, first of all, I will talk about NumExp, which is a library that allows to do quick and easy to use evaluations of NumPy operations. And then Cython, that as all of you know, that is a language that is very similar to Python that allows to reach C speed in most of the cases, if you are using Cython well, of course. NumPy is just great for many use cases. Okay, it can vectorize most of the operations, but however, there are NumPy also has some deficiencies. The most important one, in my opinion, is that NumPy has to follow the Python order to evaluate expressions. And I will try to explain you why this is a big problem. Okay? Another thing that NumPy doesn't support is, right now at least, is support for multiprocessors. Okay? So multi-threading. Except if you are linking NumPy with BLAS libraries, that comes with this support. Okay? For example, Intel NKL or Atlas or other BLAS libraries. So this is where NumExp can help. NumExp comes with a just-in-time compiler that analyzes the expression and can rewrite the expression in an intermediate code. And this intermediate code is being executed by a virtual machine that comes with NumExp. Okay? And this virtual machine evaluates the expression and returns the result back to the Python space. It also supports extremely easy to use multi-threading, as we will see in our tutorial. Okay, so let's go with the first exercise. Let's suppose that we want to evaluate the next polynomial. There's third degree, the polynomial, in some range, -10 to 10, okay? Using up to 10 million points. And let's do that using both NumPy and NumExp. The idea is to do comparisons between the speed of NumPy and the speed of NumExp when evaluating this, okay? And as I already mentioned, NumExp has support for multi-threading, and it is active by default. So in order to compare apples with apples and peers with peers, we may want to deactivate the multi-threading capability of NumExp, okay, in order to do better comparisons. So the way to do that is to set the number of threads in NumExp equals to 1. That way, it will only use one thread. So, what's this? So, enter the IPython console, and then just import NumPy. And first create the X vector with the values in which we want to evaluate the polynomial. Linspace, between -10 to 10. Oops. And we want 10 millions of points. Okay? We have here our x vector. And then let's evaluate the polynomial. I've already introduced the Python version of this polynomial. It's here, 0.25 by x raised to 3 plus 0.75 x raised to 2, etc. Okay, we have already evaluated the polynomial here. And we have a look here, and we can see the values. So let's do a timing on how much this takes. We are going to use the magic time command of NumPy, of IPython. And IPython is telling us that this computation with NumPy takes 1 second and 23 centiseconds. So let's go with numexp. Just import numexp. And then using numexp is really easy. You only have to convert these expressions to a string, in a string format. You only have to put expressions in a string format and pass this string to the evaluate function. So let's copy this. And let's put that in another vector, which I will call IP. Okay? So IP looks very similar to this one. Let's make sure that both outputs are the same. We can use the allClose function in NumPy. So allClose is telling us that Y and YP are the same array, in fact. Okay, so we have evaluated exactly the same thing in both cases. Yeah.
They're not exactly the same out arrays. They aren't exactly the same. I've got at least one false in my comparison.
They are exactly the same, yes.
No.
In your case, no?
No, I've got one. All close, yes. But if I do yp equals y, all, it says false.
Ah, yeah. Why? Why is this?
Why exactly?
You can.
But that's for me to figure out.
You know, floating point, it's very tricky. And whenever you do comparisons between different floating points values, you have to make sure that you want to compare only until a decimal point, because the representation is not always exact. Okay? So be careful when you are doing comparisons with floating point, and always try to do the normal way to do these comparisons is to, for example, to rest, to subtract the different values and to compare with an epsilon. If the result is larger than epsilon, they are not equal, but if the rest is, or the outcome is less than this epsilon, they are the same thing. So this is mainly floating points artifacts. Okay?
Okay, so artifacts should be the caching on the CPU with a different register size or a different order of computation.
Maybe it's different order than computation, yes.
If one is using SSE and the other is using the IPU, things like that.
Yeah. Okay, so let's do a timing for numexp. Oh, sorry. This is I forgot to set the number of threads to just one. Okay, so numexp is taking only 19 centiseconds, while NumPy is taking more than 1 second. Yeah? Sorry, can you speak?
Why are we doing this as num threads?
Num threads.
Yeah, why?
Why I said num threads? I said num threads because by default, numexp only by default uses all the cores that you have in your machine. But I want to do good comparisons. I want to compare apples with apples. So if NumPy is using 1 thread, let's force numexp to use 1 thread. Yeah. Okay, so we can see that numexp can do the same operations more than 6 times faster than NumPy. Okay, that is a pretty amazing result, and well, we must find an explanation for this. Anyone can suggest an explanation? In this case, why numexp is so fast? If it is doing the same operation, evaluating the same polynomial, and it's using only 1 thread? Yeah.
The Python version was creating these intermediate objects that were NumPy arrays.
Okay. This is one of the reasons, but this is not the main reason in this case. There's another one, yeah?
Computing x cubed involves computing x squared as an intermediate result, but NumPy might have been doing that twice, whereas this might have been smart enough to cache x squared on the way to getting to x cubed.
It has something to do with the x cube calculation, but it's not this thing. Another, yeah? Yeah. You are closer to the solution. Yeah. In fact, it's something like this. Yes. Another. Not pure assembly, but yes. The solution is that numexp comes with a just-in-time compiler, as I said. So what numexp is doing is to transforming this expression here to this expression here. Okay? So the thing is that the exponentiation, the x raised to 3, takes a lot of time to compute. Basically, what NumPy is doing is to call in the power C function to evaluate this one. Okay? And this power function takes a lot of time to evaluate. You cannot, the CPU takes a lot of time to compute this power because it is not implemented in hardware. So these kind of functions are typically implemented by C libraries and implemented by computing the sum of expansions of Taylors. Okay? So what numexp is doing is numexp realized that this exponent is an integer, okay, and it can transform this expression into this one. And the multiplying operation in CPUs is just one clock cycle, okay? While this kind of function calls takes typically tens of thousands or or hundreds of CPU cycles, okay? So in this case, this is why numexp is so fast, because it's doing this kind of transformations automatically for you. Okay? So, well, let's continue and let's get right. If the power takes so long time, let's avoid our power operations and we can rewrite our polynomial in this form. Okay? This is called the factorized form of a polynomial. We don't have any power call here. So if we rewrite our polynomial in this form and redo our computations, okay, in this case, NumPy takes more or less half of the time that it took before, because it doesn't have to evaluate the power expression, the power function. And if we do that with numexp, what do you think? We will get an speed up, or we won't get an speed up? What's your guess? We'll get, right? No? You think no? Okay, so let's compare with the previous form. In fact, we did. Okay? So yes, we did, because numexp, in this case, this form of the polynomial optimizes the number of operations. And it is faster than this form, because in this form we are doing more operations. So yeah, it evaluates a little bit faster, but the important thing here is that we still have an important speed up of numexp in regard with NumPy. So numexp is still 4 times faster than NumPy in this situation. Okay? So that lets us, well, this is the timing for the first version of the polynomial, and here is the second version. NumPy reduces very much the speed, the time to compute the polynomial, but numexp continues to be faster. So the question that remains is why numexp can execute this expression in our case 4 times faster than using a single core. NumPy and numexp are executing exactly the same operations, the same number of operations. Numexp is not able to optimize this function anymore. Okay? And the operations are being done in C space. Okay? So this is where your solution, some of you suggested that NumPy has a way to evaluate things differently than numexp. And the way that numexp is evaluating things is by making use a more efficient use of the memory resource. So just by making this efficient use of the memory resource, numexp is actually achieving a factor of 4 more speed than NumPy. So this is the short answer. Of course, the long answer is a little bit longer. Okay? So let me introduce you the CPU starvation problem. The fact is that nowadays most of the current CPUs typically stay bored, doing nothing most of the time, even if they are computing a lot of things. Okay, so why are they doing while why they are not doing computations? Because most of the time they are waiting for data. Okay, and why they are waiting for data? Well, the thing is that this is a graph where we can see the time that it takes to transmit a data, an element from memory to the CPU, and we can see here the evolution of the speed of memory in time, starting from 1982 to 2007. Okay, and in green we can see the evolution of the CPU speed. As you can see, both speeds are drifting away slowly but consistently through the time. Okay? And nowadays, we have a very big gap here. So CPUs run much faster than memory can provide data. Okay? And this is basically technological limitations. You cannot make memory that runs as fast as CPUs. Because if you do that, you can do that. But if you do that, memory would dissipate a lot of heat. Enormous amounts of heat. And this is not practical. People prefer to have a much more bigger memory, even if the memory runs at a lower speed, than to have a small amounts of memory, even if this memory runs much faster. So the status of the CPU starvation problem in this year is that memory latency is much slower, as much as 250 and 50 times slower than processors. And memory bandwidth is improving at a better rate, but still it is slower than processors in a range between 30 times and 100 times. And this is a huge mismatch between CPU processors speed and memory speed. And that creates a lot of problems when you want to get your programs optimized. The problem is so huge that people is writing entire books about this problem nowadays. This book is from 2009, and it is called The Memory System, and the subtitles, I think, are strong enough. So you can't avoid it, you can't ignore it, you can't fake it. You must be completely aware of this problem if you want to get the most of your systems. So vendors realize that many time ago. So this is why they introduced the cache, the CPU caches. Okay. So the idea of the CPU cache is to introduce some part of the memory and move this part of the memory directly to the CPU. And the idea is that as these caches are closer to the processor, both the latency and the throughput are much more better than memory. However, the faster the caches run, the smaller they must be because of this power dissipation problem. And here it's a graphic of the evolution of the architectures of in the 80s. A computer architecture was very simple. Was the mechanical disk on the top. Here it was the main memory, and here was the CPU. Okay. By this time there was not a mismatch between memory and CPU, so the caches were not needed. In the 90s and 2000s, vendors started to introduce a couple of levels of cache in CPUs. And we are seeing now is this kind of architectures, okay? 3 levels of cache in processors are quite common nowadays. Then there is the main memory. Another new level is the solid state disks that in many cases, in my opinion, will work like as a cache device for mechanical disks, okay? So we must be aware about this kind of architectures if we want to get the maximum performance. So in order to get this performance, we have to know, yeah. Sorry.
Which memory there are you talking about? Like that's at the end there, is that cache?
The blue line. Yes, this is where microprocessors, multiprocessors, multicores started to appear. So this is a corrected line. This is a correction of this green line, corrected by the number of CPUs that can be fit or the number of cores that can be fit on a CPU. So if you have, for example, a CPU can run at 3 gigahertz, if you have 4 cores, the equivalence is 3 by 4, which is 12 gigahertz. So this is kind of an effective cycle time. Okay? 4 cores needs much more memory bandwidth than one single core. Okay? So when caches are effective, mainly in a couple of scenarios. The first one is when there is time locality. That means that the dataset is reused. And the second one is when there is a spatial locality. That means that the dataset is accessed sequentially. Let me explain this with a little bit of detail. Let's suppose that we have a very big array in memory here, and we repeatedly access to these 4 elements here. Okay? The first time that we access these 4 elements here, the CPU needs to fetch the elements directly from memory, and that takes a lot of time. But the second time that the CPU is accessing these elements are already here in the cache. Okay? So the next time that the CPU needs these elements, it only needs to go here in the cache to fetch the elements. Okay? So it's much faster. This is the time locality. The spatial locality is a little bit different. The spatial locality means that you have a privileged direction in your arrays. And fetching data from this direction is much faster than fetching data in another direction. Okay? Because this is the way that the architectures are being implemented. Okay? So if you travel, for example, for a C array in memory, this privileged direction is the row-wise direction. So whenever you have to travel, to visit different elements in an array, please always do that in the row-wise direction. Because this is the way where the system can provide you the data faster. Okay? Okay. And lately, there are specific hardware implemented in motherboards that can detect the patterns where you are, on how you are accessing data, and they can prefetch data even before you are asking for that data. But that only works well if you are traveling in this privileged direction. So one very simple technique to take advantage of these localities is the blocking technique. The blocking technique is very easy to understand. For example, you have a couple of data sets in memory, dataset A and dataset B, and you want to operate with these data sets. What you should do is to divide the data sets in blocks that fit perfectly in cache, okay? Transfer these blocks into the cache, and operate with them. Okay? Of course, the blocks has to be fetched in the privileged direction, and once the blocks are there in the cache, operate with them as much as possible. And when you completed all your operations, and when the result is done, just put this block in the final destination. Okay? So this is basically applying the temporal and spatial localities, this technique. It's not very difficult to implement. And in fact, this very simple technique is what NumExp is applying in order to compute expressions. Yeah? In other, this? So, the in place?
Instead of allocating a third chunk of memory for the output, you just reused it from one of the...
You are meaning in this slide? in place. No, I am not using in place here. I am just this. In fact, you cannot manipulate the cache. You as a programmer, you cannot access to the cache directly. So you must trust that applying this blocking technique, the system will do the thing that they have to do. And the thing that they have to do is, if you are accessing this block, the system will transfer this block much more faster than if you access the blocks in this direction, for example. Okay? But you cannot manipulate the cache directly. Okay? Yeah? 10 minutes? Okay. So, so this explains why NumPy is slower. NumPy has to follow the Python way to evaluate expressions. And for example, when we are evaluating A by B plus C, we have 3 arrays in memory, big arrays that doesn't fit in cache normally. And Python forces NumPy to compute first A plus B and to store this in memory, completely in memory. This is a temporary, okay, in memory. And then use this temporary combined with C in order to create the final outcome that is in memory too. Okay? This is the way how NumPy works. However, NumExp works by applying the blocking technique. What NumExp does is to transfer or to use different blocks of memory of the different operands here, transfer them to the CPU cache, do all the operations in cache, and when you are done, you transfer the resulting block into the destination. The net result is that you don't have to transfer very big data sets, temporary data sets to memory, which is what is slowing down NumPy in this case. The problem is memory access. Okay? Okay, so I don't have a lot of time now, just showing a little bit about the multi-threading capabilities of NumExp. And just let's redo the computations, but using more threads. Let me select two threads. My laptop only has 2 cores, so 2 threads is the optimal configuration. And we can see that the time that it takes to compute has decreased from 19 centiseconds to 13 centiseconds. And this is very easy to use. You only have to call this and just select the number of threads you want to use, and you are done. And NumExp will respond automatically doing this. So here we have a plot, we have a bar chart where I display the time that it takes to evaluate different forms of the polynomial in terms of the number of threads. I have used here a machine with 2 processors, with 4 cores each processor, but the processors were Intel, so Intel uses hyper-threading, so the system, the processors are saying, the system is saying that you have 16 processors, okay? But these processors are logical, are not physical. The physical ones are up to 8, okay? And you can see here how NumExp scales pretty well until we get a kind of a plateau here, okay? Why do you think we are reaching this kind of plateau? Can you have a guess? Yeah?
Because it's already utilizing the whole CPU, they're not going to get any performance increase from any leftover logical space.
Yeah, this is one of the explanations. But even here, when we are using between 5 and 8 that are physical cores, the speed doesn't increase very much either. In this case, look at this way of computing the polynomial, this is not computing anything at all. This is just doing a copy of the x-axis of the x values to the y values. So in this case, we are not computing anything at all. Okay? So in the yellow bars, you can see that we are getting improvement here until we cannot go faster. Yeah. This is a memory bottleneck. Okay? So you cannot, your efficiency cannot grow below this level. And here's a comparison between numexp and a pure C implementation of this polynomial, this version of the polynomial, and using OpenMP in order to parallelize the computation. So that actually means this is a completely optimized version. So this is a representation of how numexp can perform, and generally can perform around twice as slower as an extremely optimized version, C version of your problem. So a factor of 2 it's very nice, and you know, Numex comes with a virtual machine, and when you have a virtual machine in the middle, you always have an overhead. Okay, you cannot reach this performance because of the virtual machine overhead. Yeah. Yeah, I think it's an error of the projector. No, sorry. Okay, so let me finish. Well, in this case, we are computing. This is a CPU-bound operation instead of memory bound, which is the polynomial. And for CPU-bounded operations, the scalability of numexp is much better. Okay, you can see that. Even we are having a small increase in speed when we are using hyperthreading. So hyperthreading is not a completely hype thing from Intel. For some problems, it works. For example, here we are having more or less a 30%, 40% of improvement in speed. But it works mostly for CPU-bounded problems, okay? Not for memory-bounded problems. Yeah? Sorry, I cannot hear you. Yeah?
Using the num expression built against the Intel math kernel library?
No.
Vector math library?
No. I am not using the vector math library, yes. His question was if I am using Numex can be compiled against MKL Intel library that can accelerate this kind of expressions, that has transcendental functions, okay? But in this case, I haven't made use of this capability of numexp. Maybe if I would have made use of that, the speed would have probably halved, or maybe even more. So the speed would be much better in that case. Okay, so Numex also has limitations, of course. And Numex is you can only apply Numex when you have element-wise operations. Now, element-wise operations means that when you're in loops and you want to vectorize them, you can only use the elements that shares the same index in the loops. Okay? For example, if you are trying to do things as easy as this one, you cannot use Numex because you are trying to use an element which is not in the same row than the others. Okay? And for these kind of situations is when Cython is very useful. Cython can cope with this perfectly. So I am not going to cover Cython at all because Ian has already talked extensively about this. But I can show you a final slide where I compare the performance of NumExp, Cython in parallel using OpenMP, as Ian has shown, and the extremely efficient, the best version of C that I was able to come with. And this is for evaluating this polynomial here. And we can see that in general, Cython parallel, when using only one processor, has some overhead with respect to the C implementation. But when you start to use several processors, the performance of Cython parallel, it's very close to C open to the maximum performance that you can achieve. Okay, so Cython is very nice to use when you want extreme performance. Okay, but NumExp is not doing bad. It takes just maybe it is just two times slower than the best performance that you can achieve with these operations. Yeah.
Cython and C versions, are they respecting cache sizes?
Yeah, no, it is only element by element. Okay. So the block size is just one. So it's using the blocking technique, but the blocks are only one element, of course. Okay. It's single loops. Okay. Yeah. So the final points to remember. We have to be aware that modern CPUs are starving for data in many situations, and these situations are growing fastly because of this gap between memory speed and CPU speed. This gap is growing. Memory optimization is critical for achieving high performance, and finally, multithreading helps you getting more memory bandwidth. I haven't shown you, but this bar plot is interesting because it shows you the memory bandwidth here for computing this. And we can see that when we are using only one processor, the memory bandwidth for doing just a single copy in very optimized C code grows with the number of processors, of threads. That's a very interesting thing, because I would have said that even if you are using one single thread, you would be able to reach the maximum bandwidth of the system. But it turns out that this is not the case. I am not completely sure about this result. Okay, maybe there is some architecture things that I am not understand very well, but this is what the experiments say. Okay, when you use more threads, you can get more bandwidth. At least with this architecture, which is a nice result. Okay, so just remember that NumExp helps solving the problem that NumPy has for evaluating complex expression. And the advantage of NumExp is that it is interpreted, and it also has some limitations. And Cython is there when the limitations with NumExp appear, or when you cannot apply NumExp, and you can reach near perfect speed. However, Cython is compiled. So you can choose which one you want to use. Okay, so I am done with my presentation, and now it's the turn for Mark. He will be showing you very nice plots about velocity fields and particles. You will enjoy it for sure. If I recompile what?
If you do in-place operations, a whole string of them, you end up with almost exactly the same performance as single-threaded NumExp.
With NumPy, you mean? Yeah. In place? No.
There it is. 22 milliseconds instead of 20 milliseconds.
We can discuss about this. Okay, let's discuss about this. But first,
somebody answered a break. I mean, go go ahead and take a break. There's quite a bit to cover, so but
You guys have been sitting for...
you've been sitting a long time. Take a break.
Yeah, exactly.
Keep it to 5 minutes if possible. But if you need more time than that, he'll be setting up and kind of doing a little bit of demo.
Hopefully everyone's filtering back from the break, got a breath of fresh air. So my part of this tutorial will be to basically do a worked example of a HPC style thing that someone might do. And in my example, I'm combining it with some graphics. And I'll tell you at the beginning that the particle viewer I've got up here, it's 100% Python code written with the QGL widget in PySide and PyOpenGL. So I didn't write any C, C++ code to make that do what it's going to do. And similarly, like everything else you're seeing, it's all in Python except for one helper function that I wrote. I wrote a ufunc in C++ to make some interesting noise to add some interest. But other than that, everything you're seeing is Python. So what I've got this set up here a little bit. These first 3 cells I've already run, and originally I wanted to let you guys run it with me, but I did some tests on people, and like the dependencies and everything ended up being a little bit too much to get it started. So I decided I'll just demo it for you, and we'll probably put this code up somewhere, and I'll package it up a little bit nicer later. So what I've got to start is a particle window, which I've called PW here, and I'm assigning a particle parameter object inside that window to P, so that basically we're going to interactively manipulate P and see what happens on the viewport basically at the same time. So to start, we're doing an ODE solver, and we want to do it on some kind of vector field, a velocity field. So we need to start with some velocities. We'll do something really simple to begin. So this constant field is basically going to be, or is a ufunc, and we assign it to p.field function, which is where all of our velocity fields will go. And in this case, chord is an array of particle positions in 2 dimensions, or positions in 2 dimensions for the visualization of the field. And to get the constant field, we basically want to create a NumPy array which matches it, and then we just assign the constant value, in this case by a simple multiply. So the other thing we need to get started is some particles. So I'm going to plop down some random particles. So they're in green in our viewport. And what I'll show you is that we can basically manipulate these programmatically here. So what I've done here is calculated the center of our bounding box, and I'm just going to assign, say, the first 5 particles. I'm going to manipulate the y-coordinate. The last 5, I'm going to manipulate the x-coordinate. And so it's like they just jump around. Or if I pull up the Qt console, which is basically what Travis showed you before, I can do p dot like 0. I think I should be able to assign it to something, and it should jump around. I don't know, you might have missed that. Or there's a selection feature, so I can do a particle selection where it's like, let's say I want to see particles 0 and 5 or 4, and they change color. So I'll use that a little bit later to emphasize some points, but I just wanted to show you this kind of workflow where we've got this interactive viewport that's updating at 33 frames a second, and we've got a notebook and a terminal, and we can work with it all together at the same time, and it's all fluid and interactive. And let's get into the ODE we're solving. So we're basically just going to push the particles around with the velocity. So you just think of that intuitively. You don't have to, we'll do a little bit of math there, not too much. But this is the forward Euler method to solve it, implemented in pretty straightforward Python. And you've heard a couple of times already today about how, especially since the coordinates are a NumPy array, this is a bad idea. But this is the most intuitive thing to start with. You loop through all the particles and you update each one. So the field function is that what we defined back up there, this constant field. So for each particle, we get the velocity, we multiply it by a time step, we add it to the coordinate we're looking at, and testing? All right, we're back. Dead battery? All right, so this P object, our particle parameter object, has an advanced PRT function, which we assign this forward Euler solver to. And so let's start that, and our particles start moving. So this viewport is actually interactive, so I can like drag it around and look at where the particles are going. But, there we go. I can zoom in and out and, yeah, see the particles just kind of drifting away. But let's say we look here, and there's our 10 particles, and if we just update that, you can see them updating. I guess I'm just showing you lots of different ways that this is interactive. But that's kind of a boring velocity field. It's just they're all going in one direction. So I've created this curl noise field. So this is basically putting together two ideas. So there's two important people to mention that are behind this. One is Ken Perlin, who invented it, and it's called Perlin noise. That's going to drive it. And he actually won an Oscar for it because it's very, very much used. See, there's our particles. These are still the same particles, and now they're just kind of drifting around in this field. But so Ken Perlin won an Oscar award for it, so I mean, the movie industry appreciates researchers when they make stuff which looks cool, and Robert Bridson kind of combined this idea together with taking the curl of a field, and in this case it's one field in 2 dimensions, and you can do it in 3 dimensions. And if you read this paper, there's a lot more details about how you can combine things together and modulate the noise and actually make it move around objects completely procedurally. It's very, very cool stuff that makes nice looking pictures. So this is, okay, let's just restart the particles and go back to our home base so that we're not like way off from where we started. And since this is an HPC tutorial, that's like 10 particles isn't very good. Let's do a few more. Let's start with 100,000 particles and see what happens. And you can see that's not very good. 1.7 seconds to update and 0.6 frames per second, that's not very impressive, right? But like I said, we're doing a loop in Python. And the first device is vectorize. And in this case, it's just dead simple. To vectorize that, all we do is apply this function, and now it looks a little nicer. So yeah, so you'll notice we're actually a little bit slower than we were when we were drawing nothing. Now we're at 29.8 frames a second instead of 33. So there definitely is some overhead to this, and it's taking 17 milliseconds each update step. So I should mention a little bit more about the update step, the particle advection, because that is only the computation that is moving the particles. I wanted to isolate that because the frames per second includes both that step and the rendering step. And especially once we get to higher particle counts, that's going to be non-trivial. So I was kind of making this all about the particle update step, and then the rendering is sort of just part of the display. But I'm going to shift gears a little bit and go to a little bit of a numerical analysis kind of topic. I won't go too heavy into math or anything, but there's a really serious problem with forward Euler, and we can see it with a spin field. So I'm going to make this, like, if you have a circle, a coordinate on a circle, it's quite easy to construct the tangent vector by like flipping the coordinates and negating one of them, and that's exactly what this does. It's very simple. And so there's our rotating field. So that's not bad, it rotates, but what's actually not so good is it's inaccurate, and it gets inaccurate very fast when we increase the time step. And I can illustrate that by decreasing the frame rate. So now if we're at 5 frames a second, you see suddenly it's just like, it's not spinning in place anymore, it's just blowing up. And that's the standard expectation that people doing this kind of numerical methods have for forward Euler, and this is a pretty good way to illustrate it, I think. And if we go back to this field, you can see that anywhere you have a vortex, like here, it's spinning around, the particles kind of get pushed away. And I should mention one property of this velocity field. It's divergence-free by nature of being a curl field. So that should not happen. The particles should just keep spinning around in the same place forever. But because of the inaccuracy of forward Euler, they just diverge out pretty fast. And let's say I switch to a faster frame rate, you might think, well, that's better. But let me select a few particles here, and then we can just kind of watch what happens to them over time. It's like it's better, but like how good are they going to stick around? So I'm going to go over this part pretty quick. It's basically the math of the forward Euler method. This is the ODE that we're solving. It's basically just the velocity of the particles equals this field function. And this is an autonomous system. There's no dependence on t. A lot of systems you'll want to solve like this will have the velocity field changing over time. And to solve it, basically we split up time into a bunch of time steps. A sample of times, each one is increasing. And then we want to solve like the x of t at each of those time steps. But we don't know the answer to that. This is an initial value problem. So our x0 is exact, but we're going to approximate x1, approximate x2, etc. And in our example, the time samples aren't evenly distributed. Each time might be different. And I can illustrate that by just like shaking the window, and you look at the frame rate, it's bouncing around. The code is actually taking that real time step and feeding it to the algorithm. So even when I'm doing that, it's not stuttering or anything, because the time step is getting bigger, and it's just solving for the bigger step that it needs to do. And anyways, now you can see that we've waited long enough that the particles have like even left the vortex they were in, some of them. So yeah, like basically this forward Euler method, even if you increase the frame rate, it's not gonna perform very well over time. So one of the standard, so here's a Taylor expansion. Taylor expansion is what you apply, but let's jump ahead a little bit and look at this as a picture. This is what the forward Euler method looks like with a really large time step. We start, this is our xi, and we want to solve for x at the next time. And this is the correct answer. It should follow the arrows very nicely around in the circle and land there. But what we did is we took the velocity, we multiplied it by the time step, and we just jumped straight. So how do you improve that? One way to improve it is to break it down into more steps. You could, say, do 2 Euler steps, where you go to here and then you go to there. But if you're doing that, there's better methods, and there's a whole family of methods called Runge-Kutta methods. And I will just show you one of them, RK2. Forward Euler is RK1 in that family. So basically, if you look at where you want to go, it's like the best velocity you could pick is somewhere in the middle here, right? Like that's basically pointing in the direction that the whole thing went. So how do we approximate that? How can we get that? It's basically we do an Euler step halfway, and we get this guy, and we measure the velocity. That's this light gray vector here. But then we take that vector and we shift it over to the original point here and apply it, and that plops us down right there, which is a lot better. It's still a little bit off, but it's a lot better. And here's a simple NumPy implementation of that. So you can see at first we just take the coordinate and add half a time step. And then we apply the velocity at that new position to our coordinate. And let's take a look at that. And let's go back to our spin test at 5 frames a second. So if I let that just sit there a bit and spin around, you can kind of notice that it's not blowing up like it was before. This is what reading your textbook about numerical analysis or ODE methods is good for. It will tell you these methods if you have this kind of problem to do. And I think in practice, for real accuracy, people go to RK4. It's like even this isn't enough, like in many scientific applications. Yes?
So this will eventually blow up, presumably.
Yes, because you can see there is this slight divergence here.
And it will just take a longer time. And with RK, because I'm not familiar with methods.
Yeah.
With RK4, does it end up blowing up, or is that?
These are all numerical approximations. So it's basically like a polynomial approximation of what's there, and especially if you don't have an analytical function that, like, say, whose Taylor expansion like cuts off pretty quickly, you'll always have inaccuracies. But like, let's say you're doing a multi-body simulation with like lots and lots of bodies, and you use RK4, generally the velocities and accelerations will be changing pretty slowly, and you will get quite good accuracy out of it. Like the noise field, actually, there's another factor, is like the length scale of your scene starts to come into play, because locally it does look polynomial-like, but then you start to go farther away and it's just arbitrarily changed, right? So in situations like that, you use the length scale of your scene to substep, because using this kind of more derivatives method isn't going to follow around these curves, so you kind of have to combine the higher order methods, which are good for these smooth changing fields, with substepping, which is good for this fine detail. And yeah, it can, like anything, it depends on your data and your application, and it's one of those things you have to tweak. Yeah. Does anyone else have questions? Like, feel free to ask as I'm going, or just watch it spin. But let's see, what was next? Yeah. So let's switch back to this noise field and find ourselves a vortex. So where was, so there's a good one. So we see it spinning around. If we select our particles in the middle, those should kind of stay where they are. And you can see it's not doing too bad. We're only at 5 frames a second, and it's basically sticking around. And if you are, I'm just using NumPy arrays for this, yeah. Well, that's the kind of thing that would go into SciPy. Does SciPy have anything, any of these solvers? Yes, okay. Yeah, SciPy has this stuff. No, I just did some pretty straightforward things here. Like RK1 and Forward Euler are really simple, and I guess I made the math section relatively short and got into like caches and stuff and GPU stuff later, so I didn't dig too much into SciPy and all of that. Yeah, so you can still see it's maybe diverged a little bit, but it's still basically in the middle. And I'll remind you a little bit of what Forward Euler looked like by switching back and take a look at what happens there. It's not taking too long, and now basically that's starting to empty out. So it's a huge difference, and the difference is big O delta t versus big O delta t squared. So that means if you have the time step with Forward Euler, you get double the accuracy. With RK2, you get 4 times the accuracy. So it becomes very sensitive to time step, and shrinking the time step improves your accuracy a lot once you're using these higher order methods. And so I'm going to start getting into some performance considerations with this. That's why I've put this frame rate and this timing up here. So this is RK2. It's taking about 35 milliseconds. Forward Euler taking about 17. So I don't know if any of you looked at the code and thought about that question, like what is the performance difference? So you measure it, it's about a factor of 2. And when you look at the code, you can see that the first line of RK2 is basically a Forward Euler step, but with half a time step. And the second one is another Forward Euler step, but using a different velocity field from somewhere else. So that makes perfect sense, 2 times speed. But I will be measuring a lot more stuff starting with this cache section. So I've done a little benchmark in NumPy to basically demonstrate what the linear memory access cache behavior looks like on this particular laptop. So the CPU on here, it's quad core. It's got a 32K L1 cache, a 256K L2 cache, and a 6 megabyte shared L3 cache. And you can't see the L1 cache here. This is Python NumPy code. There is overhead that's happening over here, preventing L1 cache from really playing a role at small numbers. But L2 cache has a nice little drop here, but it's not very big. And then L3 cache has a big drop, about a factor of 2. So you might ask, well, Francesc said 250 to 500 times difference, right? This is a factor of 2. Well, that's because that was a different characteristic. This is bandwidth. If you're just streaming data from memory to the CPU or back, it's very predictable, and the CPU and RAM is very good at flowing your data and pushing it over in huge chunks. This is as opposed to latency, where the gaps between this would be much bigger. But this graph is a good thing to keep in mind, and I think I'll go over a few examples. I'll try to be quick to give Travis enough time to talk about his stuff. But this graph is the thing that you should take away from my talk as the most important thing to think about when you're writing code, whether it's in Python, whether it's using NumPy, whether it's in C. Having this kind of picture in mind is really important. So, here we go. Let's do a little bit of a detailed analysis of the Ford Euler in our 100,000 particle case. So I've copied the code here again, and you can see I'm using 32-bit floats throughout, and the reason I did that is so I could have a little bit of a fair comparison with CUDA later. Doubles are reportedly not as efficient on the GPU yet. But this whole slide, if you look from the top to the bottom, it's like breaking down this single line of code into a bunch of substeps. It's like, this is basically what the bytecode of Python is doing. The first thing that's going to happen is this field function is going to evaluate at chord. And that's going to return a new temporary. So allocating the temporary gives another 800K of memory. And in doing this operation, it's going over 2 arrays at once, and it visits 1.6 megabytes of memory. So this multiply does the same thing. DT is only one value, so it's not a big array. Yes?
I've heard the word ufunc several times. I've seen the documentation. What the heck is a ufunc?
A ufunc is a NumPy element-wise operation that basically has certain broadcasting characteristics. So like you multiply different arrays together, it calls a multiply ufunc, and if one of them is one-dimensional and another is two-dimensional, there's certain rules with how that one-dimensional one extends to 2 dimensions so that it can be multiplied element-wise, yeah. So this is basically the same characteristics as a field function call. And now we don't need temp1 anymore, so that gets freed. And we do a final add, and that doesn't make new memory because we're doing it in place, but we once again touch 1.6 megabytes of memory, and we free the last memory. So if you do a lot of vectorized NumPy style programming, this is the kind of thing that should be going on in your head of like imagining where things are getting allocated. It's like, this looks so simple, but it's like you look at it and you're like, okay, there's a temporary, there's another temporary, and here it's being assigned in place, so we're skipping a temporary that, yes?
I totally agree with, you should think through how this kind of memory that you're touching.
Yeah.
Do we have any visualization tools that help us picture this?
Are there any visualization tools to help us do this?
Any of tools that help me think through how much memory I'm touching and the complexity of the operations that are performing on it. I covered profiling this morning.
Yeah.
It's exactly the kind of thing where I draw a blank and I just have to draw diagrams and that takes forever. And I miss something because I'm human.
Yeah, so I don't know of any, but Ian's basically making the point that this is the kind of thing compilers are doing already. Why aren't there tools which will produce like an annotated view of your NumPy execution that would show you exactly what I've written out here, maybe with color coding to make it very visible and like big red symbols where it's like, look at all the memory you're using or something. I think that's a great idea. I'm not aware of any tools like that, but I think if someone wants to do that, that's something which would help people improve the performance of their NumPy code a lot, definitely. So I'm going to introduce this idea of a working set here, which is you're touching different memory in a single computation. How much is that, all of that memory? And I've copied a diagram that Francesc made, which basically is this A times B plus C. So here the working set is these 4 chunks. And if you block it the way you described, basically you get a smaller picture that looks the same, where these are just smaller, and then you're kind of like stepping through the array in smaller chunks, and each one is like a little picture of the original one. So the working set of what we just analyzed is 2.4 megabytes, because we allocated 2 temporaries at the same time. And it had 3 loops that sweep through like a lot of this data. So just intuitively, you can imagine if that 2.4 megabytes fit in here, it would be faster than if it fits in here. So we're probably getting performance numbers that are related to this. And if we had more, if our working set was bigger, we would be looking at performance that's out here, like perhaps half the speed. Of course, the story is always more complicated, but that's a good intuition to have about what you're going to expect. So we're going to apply this blocking technique straightforwardly in Python to this, and we're going to try to hit the 256 kilobyte limit, but not quite because there's overhead. And so we've got 24 bytes per particle of working set. You do a simple division, and you get 11,000 particles, and so we're going to do 9,000. So I didn't do a graph like Francesco showed. This probably isn't the optimal, but it's like a good back-of-the-envelope calculation to get you somewhere. And so there's we've created the function. This is still forward Euler though. So look at the number, 36 milliseconds per update. And we switch to blocks, and 35 milliseconds per update. So I don't know if what I said maybe made you expect a bigger jump, but let's go back to this diagram, and like we were at 2.4 megabytes. That's right here, and we jumped over here. That's not that big of a difference. It's like maybe you can kind of figure that's the reason. So, well, this is typical, and that was my first hypothesis when I did this. And I reasoned that one way to show this would be to like increase the particle count and make it hit 16 megabytes of memory of working set. And so I tried that, and since I don't have that much time and I want to get to a bunch of other stuff, I will just show you that where am I? I got still, where's my percentage number? Oh, 3.8%, there we go. So that really didn't help. And it's like you might, well, but the theory, it's now we got the bigger jump. It should have, like, it did, not quite double, but it got bigger. We got more percentage improvement. And so that's when you look back at the code and try to figure out, well, what's going on. And we have this black box sitting in the middle of our update step. It's this field function that I wrote that's making this pretty noise to make the particles swirl the way they do. So maybe that's expensive. Do we know how expensive it is? I mean, it seems pretty smooth, but who knows? Maybe it's, well, actually, I'll just run this quick. And look at what happened there when I switched to a simple field. And that's basically an example of something called Amdahl's law, where if you're optimizing one piece of your software, if that is just a tiny sliver of your total execution time, you're not going to speed anything up. But if it's a bigger piece, then you might get a big speed up. So the way I applied Amdahl's law here is I postulated that field function was the slowest thing. And we remember that the spin field is just like switching around some coordinates. It's very fast. And switching to that, we see a much, much bigger performance boost. And I get about 40% improvement of this blocked version versus the non-blocked version, which I think is basically justifies this theory we've got about the cache and everything. And okay, I'll move on to NumExpr. So what's the next thing we want to do? This is a quad-core machine. We want to use all 4 cores. And NumExpr is maybe a good way to do that because it does multi-threading. So this was basically the simplest way I came up with to be able to apply it. So there's our NumExpr expression we're evaluating, and we're doing it in place. So you see this out coordinate. So if you want to do this in place with it, you actually have to use the latest NumExpr that's not released yet because I fixed a bug to be able to demonstrate this. But just a warning in case someone goes out there and wants to use it. But let's see what happens. So there's our NumExpr, and we're sitting at 19 milliseconds. And here's our forward Euler, and ooh, that's 12.5 or so milliseconds. What happened? Or maybe we're not using our cores right. Well, let's take a look at Task Manager. So this blocking one is sitting at like 7% on here, and NumExpr, okay, it's doing a better job of using the cores. It's going up to like 12%, 15%, but it's slower. Like what? So my lesson here for this is that always measure. Don't look at like the CPU graph and say, oh, I'm getting better utilization, so it's better. It might actually be slower even though you're using more of your CPU. And the explanation for why is pretty simple. It's that NumExpr didn't let us block in the field function evaluation. So we had to do that in a non-blocked fashion, and then we can block everything else. But so this is actually faster than the original NumPy version, but the caching effects so dominate that the multi-threading of the NumExpr part are completely swamped by the cache effects of this one evaluation and then the second. So it's important to understand and measure and try these different things because CPU caches aren't simple, but they are the most important thing to think about when you're doing performance. And so this picture here, when you're thinking about the performance of the algorithms you're doing, always think of this picture of like at what size you might hit memory in your working set instead of one of the L1 or L2 caches or L3 caches. And that's where you're going to get a lot of bang for your buck, much easier than, and if you're doing simple stuff, well, NumExpr basically gives you this for free. But here, when we're composing multiple operations, it's not quite so straightforward. So I better rush a little bit. My next part here is CUDA. So this is, once again, an embarrassingly parallel operation we're doing. Each particle is going independently, so it's like you can parallelize this very easily. So I've done this with CUDA, and I've hooked it in with this PRT params, and I guess the synopsis is that, so there's kind of our CUDA setup. I was able to, with a bit of effort, make it so that the particle data is on the GPU. CUDA operates on the same particle data that OpenGL renders with, and it never comes back to CPU memory. So I figured that should be about the optimal use case for this kind of data, right? So let's run all these functions quick. So the code is pretty simple. It's like it's got this CUDA device thing, and we've got float vectors and stuff. And I've done it in kind of a clever way, but I don't have time to go into too much detail there. But those those bits are composed, oh, that didn't work, are composed with code like this. So PyCUDA has an element-wise kernel object that you can create. And we're basically taking the strings that I just scrolled past, putting them together with this inner loop, which is basically assigning to each coordinate the ODE solver result applied at each step. And that's what the preamble is that. And then we just run it like a function with a GPU. So I've created this little comparison thing, and I'll basically just show you one case. I'll do RK2. Oh, no, I didn't run that one. I will have to do forward Euler. And I'll do noise field, which is a slightly simpler version of the noise field I was showing you before. And so there's the CPU. I'm getting like 300-ish milliseconds update, and CUDA compiles, and I'm getting 200 millisecond updates or so. So it's not that impressive, but this is a laptop GPU. I feel it's not even that hot still. And there's a lot of complexity here. I've just used an off-the-shelf function that PyCUDA provides. The GPU has a really tricky architecture with threading grids and everything, and I suspect if we were to start to dig into that, we could make it faster. Yes?
With the physics company where I was consulting before, I used CUDA. I spent 2 years optimizing their code.
Yeah.
Actually with PyCUDA and straight Python, then PyCUDA wrapping C, and then down to C. And there were several points during those years where I got the moments when I understood something new.
Right.
A coalesced read option where a bunch of data comes through in one go and things get 20% faster magically. If you're not maxing out all the calls, having removed the if statements, having strided your memory appropriately with the desktop version, which is much faster than the laptop version, running at 90 degrees Celsius trying to boil water, then you're not using it properly. But it took me like 2 years to get to that point of using it properly. It's a hell of a learning curve.
Okay.
You have to learn the architecture.
Yeah.
Until then, you get some nice effects, but there's just this massive, great learning curve you've got to climb up to really utilize it.
Yeah.
That's one thing I didn't get to this morning again, and my take-home would have been, it sounds really cool, but I've done the brain damage, and it's really painful, and you've really got to have the right problems.
Yeah, so Ian says I should spend 2 years optimizing this instead of 1 week. So there's my...
I couldn't see the code from here. Is the field equation being computed on the GPUs too?
Yes, that was actually one of the coolest parts, was that the CUDA code looked identical to the C code practically, and it worked out of the box. Yeah, but
Much faster.
yeah, I mean, this is I'm using one core, and this is a quad-core machine, so I just multi-threaded, and I'm beating the GPU already. So there's a lot of depth to making it fast on the GPU. So, actually.
Good. GPUs are, I said it in a talk, and if it shows up on video from the PyData workshop, not sure if it will. We did have people videoing it, but Wes McKinney has done a talk on GPU stats. It's on GitHub, and he has gone into not 2 years of optimization, but certainly 2 months. It's trying to get just calculation. See if that'll be a little better. Just calculation of multivariate normals and matrix products, essentially, on a GPU, and a lot of effort. All right, so hope that was okay to show. My colleagues have a lot of experience in various detailed aspects of getting high performance out of Python code. You can see that eventually Python gets out of the way, and you're just trying to get performance out of your CPU. And that's the great thing about Python, is it does get out of the way eventually. If you do it right, you don't have to be worried about about Python, but it's still a little bit clunky, I think. I mean, I think we can all agree that it's still, I mean, certainly when you get to the GPU and trying to optimize code on a GPU, it's sort of not for mere mortals. So you better have a really, really important problem you can afford to spend a lot of money on if you want to get high performance on a GPU. But I wanted to show just something I've been working on, because over the past several months, there's been a lot of dialogue with the PyPy team. You know, PyPy is making great progress, and we're all kind of licking our chops saying, hey, maybe someday we'll all be able to just write Python code and it'll all be magically fast. Some of the GPU concerns, I don't know that that'll happen anytime soon. For everybody, I think for isolated cases, it does work now. PyPy does a great job in speeding things up. But I wanted to just end by kind of, I guess, painting a little bit of a picture and showing some preliminary code about what I think is possible on the current CPython stack, using some of the ideas that PyPy has generated for taking Python code and producing real dynamically compiled machine code. This is kind of a picture of what I see. Kind of having this NumPy and SciPy runtime, it actually is a fairly sophisticated runtime that does a lot of things. People like Francesc and others have created CArray and NumExpert to try to optimize key pieces of it. But once the idea of, hey, there's a possibility I could actually take Python code and produce a machine code function pointer, where could I use that inside of the NumPy code base? What if I could just take Python code and build I don't have to compile all possible Python code. I just want to have pretty straightforward Python code become a function pointer. Where would I put that? It turns out just a little bit of thinking and you think of all kinds of places you could put that. This is just what I came up with in about 10 minutes of thinking about on the NumPy code base, where could I use a function pointer? We've already seen the ufuncs, and Francesc has NumExpert, those element by element calculations, those ufuncs. If you could just make your own function, compile that to machine code, then insert that into the ufunc runtime, you could beat, you could do certainly single level blocking, then maybe do something a little more intelligent and have more than one blocking. So there's ufuncs, there's generalized ufuncs, there's windowed kernel funcs, which don't even exist yet, but should if we could actually get Python functions stuck in there. These would be things like that convolution kernel I was showing. And not just linear convolution, but nonlinear, taking a nonlinear segment and doing some nonlinear operation on the elements of a image. Function-based indexing. Imagine, instead of fancy indexing, if you're familiar with NumPy, you know what I'm talking about, being able to do a mask. Imagine, instead of creating that mask, you create a function that produces true or false based on elements in the array, and then you select out your elements based on that function. Imagine memory filters, I/O transforms. Currently, NumPy can handle data that's out of order. You can memory map a D type on top of data that's byte swapped on disk. And before the calculations are done, it'll do the byte swap. Kind of behind the scenes, you don't even think about it. Imagine being able to do other things like transformations from IEEE, from IBM floating point. There is such a thing still out there in SegWi files for oil and gas, our oil and gas friends. They still have to deal with that. But even more things like Google protocol buffers and compression. You could have little transforms. And finally, potentially, a text reader that's very fast, because it can be completely arbitrary Python code. Reduction filters, computed columns, which is something I've been really trying to promote for NumPy for a long time. Computed column is basically a method that computes a result instead of a field being stored it's computed on the fly. But to do all that, you don't want to do that with Python code. It has to be machine code. You just don't want to be writing machine code with a compiler. You don't have to be worried about C. You don't have to be worried about writing that machine code yourself. You want to use something like a JIT. SciPy has tons of modules just begging for a JIT, the optimized module. We saw the ODE expression, the Runge-Kutta algorithms. Right now, you specify that with a Python code. A lot of times you want that JITted. You want your optimization step to be very, very fast. The ODE, there's just many, many places where it's just begging for a JIT. So, I want to talk about a little project I've started. I'm calling it Numba right now. It's NumPy plus Mamba, which is the black, there's a black Mamba, which is a fast snake. The idea behind this project is it uses LLVM. LLVM stands for low-level virtual machine, and it's kind of becoming an industry standard. Everywhere you turn, somebody in one of the big players in the industry is using it as a mechanism to generate machine code. So Intel just talked about their OpenCL SDK, which uses LLVM as a code gen step. NVIDIA, in their most recent PyCUDA, their CUDA compiler, actually uses LLVM as the intermediate code representation. So what they added to the LLVM stack is a PTX or GPU, which is their code gen. They added a back-end LLVM. So now LLVM can generate GPU code. Apple has done CLang, which many people have heard about. CLang is a C compiler, which uses LLVM as intermediate representation. So all of these large industry players are kind of gathering around this place, and they can worry about the code gen if we can generate LLVM bit code or binary assembly. So that's the task, is go from Python code to LLVM bit code, and we don't have to solve everything, not for arbitrary Python code. I'm just talking about some of those simple loops we were showing earlier. How do I just take and optimize something, produce LLVM code, get machine code out of it? So I've got a little project. I just want to show you an example of how it works now. So actually I just did this on the fly as Francesc was talking. This is in, I didn't figure out how to get my editor bigger, unfortunately. Code. So here are these expressions. So if I just define a function that evaluates that expression, if I could get that function to be machine code, and then insert it into the ufunc at the right place, so that the NumPy machinery, which inside is calling out to a machine code to evaluate some function, if I could just dynamically replace what it's calling with this generated function, then I can get really, really fast ufuncs that don't use any temporary memory at all. It only uses the temporary memory of the variables defined there. So that's what this translate module does, is it takes a Python function, takes the bytecode, walks the bytecode, kind of replays it, and produces a machine code representation of that in LLVM. So if we ran this example, and then basically it translates it. This printing is just to print the LLVM representation for instructional purposes. And then there's a make ufunc method on this object. So it gives me out a element by element calculator that will run on any array, do the broadcasting correctly, and produce the result I'm looking for this single argument ufunc. So if I run this, it's called numexpr compare. I get two things printed. If you've never seen LLVM code, this is what it looks like, at least the ASCII representation. It's like assembly, but in memory it's actually represented much more compactly. And then there's a very, very easy way to JIT this code. It just JITs really, really quickly. And so this is the assembly that corresponds to that function. Actually not too difficult. These problems aren't that difficult to solve in the small. Where they become very difficult is to go arbitrary dynamic Python code. That takes a long time. As scientists, technical people who want to I want to do this calculation fast, we don't need everything. We just need something that gets me, it's actually remarkable how little we need to get so much, and that hasn't been provided by anybody yet. I guess that's what's surprising to me. And maybe because there's so many people chasing the big dream that some of the I'll just take the table scraps in some sense, right? I feel like I'll just take the table scraps and let's put those together into a project we can use actually today. And we don't have to solve all the problems before we get something working. And what I did, this ufunc is basically for the right order. So I have now an exercise 1A and exercise 1 ufunc. And if I take X and I time it, it does a bunch of 49.4 microseconds per loop, comparing that with the num expression result. It's doing a bunch of timings. 154 microseconds. So for this particular size, it's about 3 times faster. Right? So with a simple decorator on a function, you have a ufunc that's running at machine code speeds. That's what NumBuzz is going to be, decorators on functions that give you that example that I showed earlier. where we did that simple, fast Python, and I said what I want is I want this. Right? I just want to write Python code, I decorate it, and now it understands NumPy arrays, and it converts that to machine code that's as fast as any of the other solutions. And that's days away. That's very, very simple to do. It's not years, it's days. And that's where that's what I'm looking to do, and that's what the Numba project is. If you'd like to be involved, it's an open source project, it's on GitHub. It's under the Continuum.io Numba project. So jump in if you're excited about this, and let's start making fast code. Thanks.